big N over the length. If you're in your notes, I recommend using a lowercase l here because we're about to use an uppercase L for something else. Mu naught N squared over L times A DIT. So this is the voltage that is created by the changing current in the solenoid. This part right here, that part right there, well, mu is not a constant, but N, L, and A are all based upon the geometry or how the solenoid was created. That's the area of, not the area of the wire, but the area of the hole. N's the number of coils they stuck into it, L is the length of it. This part that I circled in brown here is the inductance. Represented by a capital L. So we could figure out the inductance of this coil if we knew what the cross-sectional area was, or the area of the loop. Because an inductor is just a coil of wires, the circuit, like we have, that's a resistor representing a whole bunch of wires crammed together, so that's for resistance. Capacitor, that's the symbol, it's like you have two parallel plates. And an inductor is a coil of wires.
I'm sorry, can you explain everything in that equation again, really quick? What each variable means at the bottom with the inductance?
So that's the permeability of free space.
Yeah.
And if it's air inside, the value is close enough to that. Big N is the number of coils in the solenoid, squared. That's the area of the loop.
Yeah.
So not the wire, but the loop itself. And L is the length of the solenoid.
Area of the loop that you create.
So it would be that area.
Like the solenoid, and then it's multiplied by the changing of the current
Yes.
over time. Okay. And that gives you the whole thing is the voltage of
The induced voltage based upon the changing current.
okay.
Other questions? All right. And again, I think I know what you're thinking. You're going, hey, this is great, but where's the calculus? Yeah, well, we have a derivative over there, but didn't really do anything other than pull constants out. Let us take a look at a nice little circuit. I got power supply here. I have an inductor. I have a capacitor. I have a switch. So what I'm going to do is I am going to close the circuit. I don't care about the buildup, but this is just this is showing that current's going to flow here, it's going to go both ways, and eventually my capacitor will be charged. So this is a basic circuit to charge capacitor. And then I'm gonna disconnect. So I have a fully charged capacitor. So my circuit then looks like, once I disconnect it, this whole section over here becomes irrelevant, and I'm left with a fully charged capacitor and an inductor. And then we'll make that the positive plate and the negative plate. Kirchhoff's rules still apply. I'm gonna start here, I'm gonna work my way around the circuit. I know that as soon as I stop feeding into it, this is gonna start to discharge. I'm gonna have current flowing this way. And so if I start here, do my voltage loop, I'm gonna gain potential, so I've got some potential gain across my capacitor. And then minus, you know, the whole plus minus thing here. I'm gonna put plus at the moment, and the minus sign will show up in just a second. So whatever my potential difference across the capacitor plus potential difference across the inductor is 0. It's just, since this is positive, that's gonna be negative. This is gonna be negative Q over C. We'll put a little C next to the Q. This is the charge on the capacitor. Oh, it is positive. Minus L d I dt. And this is the current flowing across the inductor. Now I differentiate between the two because the current flowing across the inductor has to be the current that is not on the capacitor. I know that the current across the inductor is dq inductor dt. So I have current on the capacitor, it starts to come off of it, so QC starts dropping as QL starts increasing. So the rate at which current is flowing, or the charge is flowing across the inductor, has to be the negative of the charge, the rate at which the charge is leaving the capacitor. Make sure I didn't get a minus sign screwed up there. Okay. So my voltage loop here now becomes QC over C plus L, second derivative of QC with respect to time. Because that's IL then. Equals 0. So I have a second order differential equation. What is a function whose second derivative would somehow negate the start, what I started with? What function has a second derivative that has, in essence, a negative of itself? QC is equal to some function. I know when I take the second derivative, well, I'm going to have to get rid of it. I'm going to have to get rid of whatever QC is. I mean, if this is x, the second derivative is 0. That doesn't work. If this is x cubed, then that's on the order of x, and that's not going to cancel out. I need some function. When I take the second derivative, I get a negative of whatever function that is. All of you know the functions.
I'm sure we do.
Let's think trig functions. What trig function has a second derivative that's the negative of itself?
Sine.
Or cosine, whichever one you like. I'm personally, since this is QC and it starts out with a fully charged, I'm going to go with cosine. It's starting at a peak charge. So cosine, so I have some amplitude, cosine omega t. we'll assume phase is zero, phase shift is zero. If that's the case, then dqc dt is
a negative a sine wt
omega.
sorry omega and we're dt, so it'd be, oh no, that's no,
No, there's no omega pops out. Chain rule.
oh right, yeah,
Cosine, and then you do that part.
yeah, I was thinking in terms of t and then I forgot that the omega stays.
And then the second derivative, I'm gonna use the dot notation, qc double dot.
Positive a omega squared cosine omega t.
Close. Yeah, negative.
Oh, because we're keeping going, oh yeah, okay.
And also, if it were positive, then that wouldn't help us here, because then I'd have two positive terms. I need one of them to be the negative of, with a negative cosine there. So this, since this function can satisfy it, we go in with, so I have a, whatever the amplitude is, cosine of omega t over the capacitance, plus L minus L a omega squared cosine omega t equals 0. I have cosine common if I just divide out the cosine. That goes away, then 0 divided by that. I can divide out the amplitude. So I'm now left with 1 over the capacitance is minus L omega squared is equal to 0. 1 over the capacitance is equal to L omega squared. Omega squared equals 1 over LC. Omega is equal to the square root of 1 over LC.
What was omega again?
Omega is the angular frequency of this thing oscillating back and forth. So I have this charge that is going to be coming off of here and flowing. This is the charge that is on the capacitor. So it starts out at a maximum amount. So we have a formula for the charge on the capacitor, which is an amplitude times the cosine of 1 over the square root of LC times time. When time is 0, QC is equal to whatever the maximum charge is. So therefore, you plug 0 in for time, this whole term becomes 1, and so QC is equal to A, so my amplitude is just whatever my maximum charge is on the capacitor. So we're now left with the formula for the charge on the capacitor is equal to the maximum charge times the cosine of 1 over the square root of LC times time. If I plotted it, QC time, and so on. So what is happening here in my LC circuit with my nice no resistance wires is the current's the charge is gonna flow off the positive plate, come onto the negative plate, and then reverse, and then come back, and it's just gonna go on forever, because there's no resistance. If the inductor were not there, then the charge would go from the positive plate to the negative plate and be done. It's neutralized, nothing else, but the inductor causes the current to keep oscillating back and forth. Questions here? Because we're about to talk about everyone's favorite topic, units. So I like SI units. So I have omega is equal to 1 over the square root of LC. What are the units of angular frequency?
Grass a second, or radians.
You stopping at revolutions?
Oh, per minute.
Okay, revolutions per minute would be a valid one. SI units would be. I thought you were, Nick, you started to say.
Radians a second.
Yeah, radians per second. Typically, it's given in radians per second, however, revolutions per minute also works. It's the same units of angular velocity or angular speed. That's going to be equal to the square root of the units of the inductance times the units of capacitance. And what are the units, the SI units for capacitance?
Farads.
So that's equal to 1 over the square root of the units of L times farads. Square both sides, so I have a radian squared per second squared is equal to 1 over farads times the units of inductance. Multiply by that, so I end up with farads per second squared. If you want to keep the radians squared in there, you can, but usually they go away when you multiply by something. Is equal to 1 over the units of inductance. So the units of inductance would be second squared per farad. It is legitimate. We could then go for, actually from here, well, actually, let's take one step further. Second squared per farad is not a particularly convenient unit to use, and so they made up their own unit to honor Henry. So the SI unit of inductance, the one word is the Henry. And this is the one that the inverse Henry is the internet. Again, legitimate scribe word. But given that, so that means that a second squared is equal to a farad Henry. So a unit of time is the square root of the farad Henry. Not that it has any importance other than fun with units.
Oh, it's just Henry spelled backwards.
Yes, there's a, yes.
Oh, year. Is that how you say it?
I always pronounce it Earnet. I've never actually heard it pronounced.
Oh.
So if you have your own pronunciation, as long as it remotely resembles the letters there, I think you're just as valid as I am.
Okay.
So you can literally represent seconds as a square root of farad henries.
Yes.
Can you represent seconds as other things too? Probably.
Yeah.
Yeah, many different things.
Yeah, that's one of my favorite test questions of all time. It was not the student's favorite. I thought I talked about this one before. I gave them a list of 15 different bizarre combinations of units, and I said, which are units of time? And 14 of them were units of time.
Just because they had seconds in there somewhere and you could always solve for seconds.
Yeah. What I did not consider is how long it would take to do each one to revise. That was bad timing on my part.
That should be a bonus question.
I still like the question, but although there is the sadness of the number of students who missed the letter S as a unit of time. But I think there was a certain amount of their brains had turned to mush by then.
My brains feel a little bit like mush right now.
Yeah. That's why we sleep, for your brains to repair and to go, okay, that now it makes sense. Sorry, what did you ask?
Was QC charge of the?
That's the charge on the capacitor.
Oh, okay. And max is the maximum charge on the capacitor?
Yes.
Okay.
Sometimes listed also as Q sub 0 and Q sub m.
And it's just in that particular type setup?
Yeah.
The equation is applicable?
It's just for the LC circuit.
Oh, okay.
It seems like you usually see it as LC and not CL. I don't know why. We're gonna do one, we'll do an RL circuit and then, get it potentially.
So DC is direct current and then LC is,
No.
induced current?
No, LC refers to the components. I have an inductor L and a capacitor C. It's a different naming, separate naming convention.
It's still a DC circuit?
Yeah, this one's still a DC circuit.
Okay.
Well, it was charged by a DC circuit. I guess officially the current is floating back and forth, so I make an argument that it's alternating current or AC.
How come on the battery and the solenoid, we got rid of the left side?
Because if the switch is not down, then this has no purpose.
Okay.
Because you need a complete circuit, and so once I break that, there's no complete circuit, and so this would not generate any more current. So that's why I ignored it.
Okay.
All right, let us look now at